Okay. All right. So we are live doing Waves introduction notes. So I'm just going to jump right in. The PDF that I'm going to be showing is in Canvas already, along with all of the animations that I'm going to be showing in Canvas already. And the first page, unfortunately, the lettering didn't, woo, it's a little close. Lettering for some reason is a little bit like shaky. It must have just been how it scanned, so I apologize for that. So what is a wave? Well, a wave is some sort of continuous vibratory disturbance that transfers energy and not matter. So it's how we get energy from, let's say, the sun to Earth. I apologize for yawning. Or how, my sound waves travel from my vocal cords to your ears, anything like that. So it is an energy transfer method, and it comes from something vibrating initially. So when we're talking about sound waves, and specifically speaking, it's my vocal cords vibrating that is causing the sound energy to travel. When we're talking about energy from the sun, it's really electrons vibrating in their energy levels that causes the electromagnetic energy to travel. So waves come from actually a type of simple harmonic motion or a vibration. Okay. So we can kind of cut the wave down into its smallest bit, and that smallest bit would be called a pulse, which is the smallest component of a wave that results from only a single vibration. So instead of vibrating back and forth like this, just like a single boop, single pulse, like, your heartbeat essentially. Let me just go ahead and get my highlighter ready. Okay. So there's two major kinds of waves, and the wave that we're really going to focus in on in this unit is mechanical waves. So sound waves, things like that. So mechanical waves require some type of medium to travel through, and I'll talk about what a medium is in a second. Okay, the example is, I'm sorry, I'm yawning so much. The example is sound waves. So sound waves require some type of medium to travel through. The other type of wave that we could study is electromagnetic waves, and those are the waves that are kind of bouncing around in space. So electromagnetic waves are super cool because they actually don't need a medium to travel through, so they can travel through vacuum, which means that they can travel through space, which is really cool. And that's how light travels to us from the sun, even though there's really nothing for the wave to necessarily travel through, because space is a vacuum, light can still get to us because it's electromagnetic. So let's talk about what a medium is. So a medium is a continuum, or, space, like area, not space, area. A continuum of particles, so an area of particles of the same type that can store and release energy. So essentially the particles in that medium can kind of get farther apart and closer together and stuff like that, so they can store and release energy. So it's whatever solid, liquid, or gas that the wave is going to travel through. So as that wave travels through the medium, it's not going, or it will lose energy. So as a wave travels through the medium, it loses energy. But that doesn't occur in vacuum. So what that means is mechanical waves actually lose energy as they travel, and electromagnetic waves do not. So that means that mechanical waves can only transfer energy over short distances, right? Like if I was to start speaking, even if I was speaking very loudly, that sound would eventually die out. But light waves can travel, billions and billions and trillions of miles. They can travel light years. Okay, so that's like what it says here. Electromagnetic waves can transfer energy essentially over infinite distances in vacuum, which is why we can only see light from very distant places. And I'll talk about why that is in a little bit. Okay. All right. So now let's talk about how that wave energy is actually traveling. Okay. So when we talk about a wave speed or a wave traveling. It's the energy that's traveling. Remember, it's not like the matter that's traveling. It's not the individual gas particles that are traveling at a specific speed. It's the wave energy itself. I'm sorry, I'm yawning so much. Okay. So we have two types of ways that energy can travel. They can travel as transverse waves or longitudinal waves. So first we're going to talk about transverse waves. And these are kind of, if you were to picture a wave, the more common way you would picture a wave. So transverse waves occur when the particles in the medium or the energy carrying particles in vacuum, like a photon, move perpendicular to the direction of motion. So in the diagram that I have drawn here, okay, the wave energy is traveling to the right as shown, okay, but the particles themselves are only traveling up and down. Okay, so I can switch over. So here is an animation of a transverse wave. Now, the energy itself is traveling to the right across the screen, but if you pick on any individual particle, it's only vibrating up and down. And that again shows us that we're not transferring energy, or we're not transferring matter. The particles aren't moving to the right with the energy. They're just moving up and down because waves transfer energy, not matter. Now you might be thinking, well, how does that work in water waves? Because that's a little bit different, okay? Well, here is a water wave, okay? So the particle in a water wave still kind of undergoes this transverse wave motion because we still get that, like, you know, perpendicular motion. But instead of traveling perfectly up and down, the particles travel in a circle. And the particles at the top travel in a larger circle where there's larger displacement, and the particles in the bottom travel in smaller circles. So the matter itself still stays at the same location, but the energy still transfers through, okay? Essentially passing from one particle to another, okay? So transverse waves, we say, move perpendicular to the direction of travel. And the way I always remember that is the T in transverse looks like a perpendicular symbol. Okay, so let's talk about the anatomy. Oops, not letting me move. There we go. The anatomy of this transverse wave. So essentially, what are the different parts of a transverse wave? So the first two things we can talk about is a trough and a crest. Okay. So the crest, if you see it written and it's talking about the crest of a wave, the crest is just the top of the wave, essentially. Yeah, the top of a wave. There's really not much else you can explain. And then the trough is the bottom of that transverse wave. Okay. So the crest to trough area here, like if you were to measure that, that represents half of a wave. Okay. So the next thing we can talk about is the amplitude. And so we can measure the amplitude like this or like this. Okay. So the amplitude, let me here's that. Okay, so the amplitude of a wave is the height of the wave from the center line. So it's not the total height, but rather half the total height. Okay. Now what's really interesting is the amplitude, and this is really important, is directly related to the amount of energy in the wave. Okay. So the larger the amplitude of the wave, the larger the amount of energy in that wave. Okay. Now in a medium, it's that amplitude that's going to decrease as time goes on, as the energy decreases, because the particles in the medium aren't going to transfer energy completely elastically, right? Because we know that elastic collisions essentially don't exist. So that means with every bob up and down, we're going to lose a little bit of that wave energy, which is why mechanical waves can't continue on forever and ever and ever and ever, like electromagnetic waves, because they are essentially dissipating energy to their surroundings. Okay, so the amplitude ends up decreasing and the energy ends up dissipating all the way into its surroundings eventually. Okay. Then the last thing we have is the wavelength. Okay, so the wavelength we can measure from one full sine wave, one full cosine wave, or you'll see it as the distance crest to crest, trough to trough. Either way, it's the distance of one full cycle of the wave. So it is a distance measured in meters. Okay? Don't confuse wavelength and period. Period is a time to complete one wave. Wavelength is a distance from one wave. Okay? And then the last thing I want to talk about for transverse waves is the fact that they move faster in less dense media and faster in vacuum. So what this means is any type of energy that's traveling as a transverse wave is going to move slowest through solids and fastest in vacuum, where there is no medium. So light travels the fastest through vacuum, slowest through solids. I'm just going to check and see if there are any questions. And there's nobody here, so I'm going to say that there's probably no questions. All right, so now let's talk about longitudinal waves. Okay, so longitudinal waves, we have the particles in the medium moving parallel to the direction of motion. So all the L's in parallel go with longitudinal. That's how I remember it. So longitudinal waves, because they need that, they rely on essentially collisions from one particle to the next. We need to have particles, which means we need to have a medium to travel through. Okay. So parts of a longitudinal wave, we have the compression section where the particles in the medium are very closely together. And then we have rarefaction where the particles are separated out. Okay, so as the wave travels to the right, the particles in that medium travel or vibrate back and forth. Okay, and these types of waves, longitudinal waves, move faster in denser media. So they move fastest through solids, slowest through gases, and they can't travel through vacuum because, like I said, we need those particles to bump into each other. Now, the best example of this is sound. So yes, that does mean that sound cannot travel through space. So when stars explode or something like that, they actually don't produce any sound, which is really super strange if you think about it. Okay, so let's look at some animations of longitudinal waves. Okay, so here is a longitudinal wave animation. So the energy itself, if you kind of pick a compression section and follow it, the energy itself is moving to the right across your screen. Now, any of these red dots you'll see aren't actually moving to the right, they're just vibrating back and forth. And we can see that there's collisions happening, causing these objects to move back and forth with one another. So here's a slightly better animation. So we can see there's a particle, right? And here's the wave itself, and the particles are remaining stationary. It also has the compression and rarefaction sections labeled. So compression, compression, rarefaction. Now, if you wanted to measure the wavelength of the wave, you would measure the distance from one compression section to another compression section. So the compression is kind of like the crest of a transverse wave, the rarefaction kind of like the trough. Okay, and the amplitude of these longitudinal waves essentially change based on how compressed the compression sections are. So the more compressed the compression sections are, the larger the amplitude. All right. So now let's talk about this idea of wave speed. And it's going to take a second to catch up to the fact that I want it back on OneNote. Yep, there we go. Okay, so wave speed. So this energy that's traveling is traveling at a specific velocity. So no matter the type of wave, okay, the wave speed, or the wave of the energy, or no, the speed of the energy, there we go, is going to depend on the medium the wave travels through. So again, the speed depends on the medium the wave travels through. Okay. So we talked about how longitudinal waves can travel faster in solids, but transverse waves can travel faster in vacuum. So if we change that medium, we change how fast it's going to travel. Okay. So changing the medium is going to change the speed. Okay. So that means that as sound travels from water into air, the speed of the sound wave changes. Same thing with light. As light travels from outer space into our atmosphere, the speed of the light changes. Okay, so the speed of that wave helps determine the relationship between the frequency and the wavelength. Now, we talked about frequency and period when we talked about simple harmonic motion, and the definition of those words pretty much remains the same, but instead of talking about oscillations per second or the time for oscillations, we want to talk about frequency as being the number of waves per second and period being the time to complete one wave. So instead of a cycle or an oscillation, we now just throw the word wave in there. Okay. So one thing that is really important is once a wave is produced, the frequency and period cannot change, even if the medium and speed changes. So even if that speed changes as we go from water to air, even if the speed changes as we go from vacuum into the atmosphere, the frequency of that wave isn't going to change because that frequency depends on the initial oscillation that created that wave. So that's not going to change. Frequency and period cannot change because remember, frequency and period are related to one another with the equation T equals 1 over F. Okay. All right. So let's talk about this speed equation. Now, in kinematics, we talked about speed as being distance over time. That actually still works for waves. We can measure the amount of speed of a wave by the distance it covers in a specific amount of time. Or we can measure wave speed with specific information about the wave itself. So we can calculate the speed by doing the wavelength over the period or the wavelength times the frequency. Either way, the speed is going to be measured in meters a second. So all three of these equations work for calculating wave speed. Okay, so remember that frequency bit is going to remain the same even as we change the speed. Okay, so when we do change speed, it must be the wavelength that's changing. Okay, so one other thing that's important is that wave speed does not affect the amplitude and therefore does not affect the energy of the wave. So a lot of people think that the faster the wave, the more energy is in the wave. That's not true. Energy is related to amplitude, and amplitude has nothing to do with the speed. So the faster the wave travels through, or the faster the wave travels, really just gives us information about the medium, not the amount of energy the wave has. Okay. All right, so an example, let's say that we have a wave with a frequency of 1.5 hertz. Remember, that's the unit for frequency. Moving through a heavy spring with a wavelength of 2 meters, what's the speed of the wave? Well, we're given the frequency and the wavelength, so I should use V equals F lambda. Lambda is the Greek letter for wavelength. So 1.5 times 2 gives me 3. Not too bad. What wavelength would the wave need to be if it moved into a lighter spring with a speed of 6 meters a second? Okay, well, now I need wavelength. We're moving into a different medium, which is why my spring is changing, or my speed is changing. The other thing I need to keep in mind is that frequency remains the same, which is why I'm still able to plug in that 1.5 hertz. Okay, so I still have 2 pieces of information. I can find the third. So I use the V equals F lambda equation again, but this time solve for wavelength. I get 4 meters. Okay, so the medium, there we go. The medium changed such that we were able to travel faster through the medium. Okay, and that increase in speed led to an increase in wavelength. Now, this wave, because it's traveling faster in a less dense media, was likely a transverse wave. All right, so let's talk about some cool things that waves can do. The first thing is that waves, much like particles, can reflect off of surfaces and boundaries. So there's two types of reflection, and I'm going to flip on over to the animations. So the first type of reflection that a wave can undergo is reflection at a hard or immovable or dense boundary. So in this case, the wave, or what's being shown here, pulse, inverts at that boundary. It phase changes 180 degrees or flips 180 degrees, as I say. Okay? So waves come in, they bounce off, and it flips. So that's at a fixed or hard boundary. The other type of reflection that we can undergo is at a floating point or soft boundary. So in that case, the boundary position, that was a weird way to say it, is able to move along with the wave. And since we're able to move along with the wave, instead of inverting, the wave is just sent back without that inversion. Okay, so nothing really too crazy. We're going to talk about the implications of this reflection a little bit later on when we talk about standing waves. Okay. So the other cool thing that waves can do, come on, there we go, is interference, or what is also called superposition. Super on top of, position, location. So yeah. So the coolest thing about waves, and therefore energy, and this is something that regular matter cannot do, is that when waves interact with each other, they're actually able to pass through each other. So instead of like two tennis balls where when you throw them at each other, they bounce off, waves, on the other hand, can kind of just pass through each other, right? It's really cool. So there's two types of interference, right? First is constructive interference, and this is when the amplitudes add together. So let's say we have a square wave and a triangle wave heading towards each other. So they head towards each other, and then at the instant in time where they both overlap, those two amplitudes kind of combine together, and then afterwards the two pulses continue on their merry way as if nothing ever happened. The amplitude's the same, the speeds are the same, everything about those two pulses or waves is exactly the same. Interference does not change any property about the wave except for the amplitude when the two waves are actually interfering. Destructive interference is when the amplitudes actually subtract from one another. So instead of having two positive amplitudes or two negative amplitudes, we have one positive and one negative. So in this case, we again have a square and a triangle, but this time the triangle is kind of flipped from before. So in that case, the triangle section actually ends up subtracting out of the rectangular or square section. But afterwards, we still see that the two waves are continuing on, essentially unfazed from one another. Okay, so let's see some animations of that. Okay, so here is a good wave interference. So what's nice about this animation is we're shown the wave and how, or we're shown the individual waves as they're interacting. So one's blue, one's red, and we can see that this black line is kind of the addition of the two of them. So this is constructive interference because the amplitudes momentarily add. We see that the blue continues on as if nothing ever happened, and so does the red. Super cool. So here's an example of destructive interference. And this is a special example of destructive interference. It's called complete destructive interference, in the sense that for a brief moment in time, these two pulses are able to completely cancel each other out. So you can actually cancel waves out if you send them at each other properly, which is kind of cool. Now, also on Canvas, there's some cool simulations you can play with. So this first one is kind of fun. If it waves. Okay. So let's see, wave one, wave two. We can show the two colors, and we can see that these two things momentarily add together, and then they pop off. And now if you hit notes, it'll show you exactly kind of what's going on. And there's a bunch of different shapes that you could play with. So this one is two triangles that add together and so on. Now, the second one is kind of more like transverse waves. It's called sinusoidal. So instead of the weird shapes, it shows two sine waves that would either add or subtract. So these two kind of do a little bit of both depending upon how they're interacting with each other, which is strange. Okay. So here's another one. Ooh, that one's funky. You could slow it down if you wanted to. All right. Let's go back to notes. So the last thing I kind of want to talk about today is sometimes, sorry about that. You'll see questions that ask you, what is the direction of, or what direction would point A on the wave move next? Okay. And so, once OneNote catches up with the fact that I want to use it, there we go. So let's say we have a wave that's moving to the right. So this blue line represents the original wave. Okay. In order to figure out what direction the particle is going to travel next, I want to draw the wave at the next instant in time. So that's this red wave here. Okay. So I have 4 particles on the original blue wave. Now, in order to stay on the wave, they need to travel up or down to get onto the red wave. Remember, these particles only have the option of traveling up and down because it's a transverse wave. So this first particle needs to travel down to get to the red wave, then up, and then down. So not too bad to try and figure out the direction of waves. You could do the same thing with a leftward moving wave. Again, the blue is the original wave. Then I draw the wave at the next instant in time, shifted left a little bit. And I have 4 positions on the wave, and I just draw arrows up or down to try and get the particles back on the red wave using only up and down motion because we are a transverse wave. Okay. So that is pretty much it for wave motion. A fun simulation. Let's see, waves on a string. A fun simulation you can use if you just want to explore more and play more with waves is the waves on a string simulation from PhET Colorado. Make sure you're using the HTML5 version. So you can either create like manual waves, okay? And you'll notice that the amplitude sort of decreased as time went on. That's because of this damping function here. Okay? So we're essentially losing energy because of damping. So if I put this as none, then I should see no change in amplitude, right? And I see that my wave is reflecting. Okay? So I could also create pulses and just send pulses down. Woo! Okay? And I can change this to a loose end and see that there is no inversion, but this is a fixed end over here, so there is inversion, or I could do no end and it just goes out the door. And I could change the amplitude, which means it requires more energy to create, right? I'm gonna reset, oops, pulse. I can change the pulse width, which changes the wavelength. Okay. Changes the wavelength. If I'm doing oscillate, notice how instead of pulse length, I'm changing the frequency, essentially how fast this is oscillating up and down. Okay. Now, the reason you're seeing this weird pattern kind of being created is something we'll talk about on Wednesday. It's something called a standing wave. Essentially, the wave being sent down the string is interacting with the reflecting wave, trying to create something called a standing wave, which means it's looking like it's not going to travel. So if I do no end, there, that kind of gets rid of it and I get a nice wave. So again, you can see here that the particles are just traveling up and down, right? Now, if I change the tension, again, we're going to talk about this a little bit, right? It looks like the particles kind of slow down a little bit. Now my wavelength's changing a little bit. So we'll talk about how the tension is related to the speed of the wave. All right. So that's pretty much it for wave basics today. I will see you guys next time. Have a wonderful day.